At 6:23 in the morning on August 8, 1944, Sergeant Andrew Milnarczyk stood in the maintenance area of the 1st Hussar Tank Regiment near Caen, France, staring at a problem that seemed impossible to solve. His regiment had just received orders to attack the heavily fortified German positions in the Falaise pocket, and the intelligence reports described something that terrified tank crews more than anything else. The Germans had converted Norman stone farmhouses into fortress positions, with walls 3 feet thick, firing slits protected by steel plates, and interconnected defensive networks. Canadian Sherman tanks had been throwing high-explosive shells at these positions for days, and the results were minimal, as the ancient stone walls absorbed the explosions without collapsing. Infantry assaults had been bloodbaths, with Canadian soldiers pinned down in open fields by machine gun fire from positions they couldn't destroy. Milnarczyk was 31 years old, a tank mechanic from Winnipeg who had been maintaining Shermans since the regiment landed in Normandy 6 weeks earlier. He had spent the previous night reading after-action reports from other Canadian units, and every report told the same story. Conventional weapons couldn't break these German strongpoints. What the Canadians needed were Churchill Crocodile flamethrower tanks, British specialized vehicles that could spray burning fuel through the firing slits and force German defenders to surrender. But there were no Crocodiles available for the Canadian sector, as all British flamethrower tanks were committed to supporting British units farther east. The 1st Hussars would attack without flame support, which meant more Canadian soldiers would die, trying to assault positions that conventional weapons couldn't neutralize. Milnarczyk looked at the equipment scattered around the maintenance area, damaged tanks waiting for repair, spare parts salvaged from destroyed vehicles, and fuel drums stacked near the field kitchen. He had an idea that violated every regulation in the Canadian Army Maintenance Manual, contradicted his training, and would probably get him court-martialed if it failed. But if it worked, it might save dozens of Canadian lives in the coming assault, and that was worth the risk of facing charges. What Sergeant Milnarczyk did over the next 36 hours would create a weapon system that shouldn't have existed, change how Canadian forces fought in Normandy, and prove that sometimes the best innovations come from mechanics who refuse to accept that problems are unsolvable. The Churchill Crocodile was one of the most fearsome weapons developed by the British during World War II, and by August 1944 it had already proven its effectiveness in Normandy. The Crocodile was a Churchill infantry tank, modified to carry a flame-throwing system, and the modification involved removing the hull-mounted machine gun and replacing it with a flame projector. The fuel for the flamethrower was carried in a 400-gallon armored trailer towed behind the tank, and the trailer was connected to the flame projector by a flexible armored hose. The system could project burning fuel up to 120 yards, and the flames reached temperatures of 1,000 degrees Celsius, hot enough to incinerate anything in the target area. But more importantly, the Crocodile's psychological effect was devastating, as German soldiers would surrender rather than face the prospect of being burned alive in their bunkers. British units equipped with Crocodiles reported that German positions would often surrender as soon as the flame tank appeared, without requiring actual use of the weapon. However, Crocodiles were specialized vehicles that required extensive modifications and were available only in limited numbers. The British 79th Armoured Division controlled all flamethrower tanks and allocated them based on operational priorities determined by British command. Canadian forces, operating under their own command structure, had requested Crocodile support for the Falaise operations, but were told none were available. The reality was that British units had priority for flamethrower support, and Canadian requests were secondary, regardless of tactical need. This left Canadian tank regiments facing heavily fortified German positions with only conventional Shermans, and the results had been costly. Andrew Milnarczyk had joined the Canadian Army in 1940, enlisting in Winnipeg at age 27, which was older than most recruits. He had worked as a mechanic before the war, maintaining farm equipment and diesel engines in the Manitoba countryside, where reliable repairs were essential for farmers. The Canadian prairies in the 1930s had taught Milnarczyk the same lessons that Filipino mechanics learned. When parts aren't available, you improvise with what you have. Farm equipment broke down constantly. Replacement parts took weeks to arrive from dealers, and farmers couldn't afford to wait when crops needed harvesting. Mlynarczyk learned to fabricate parts from scrap metal, adapt components from different machines, and keep equipment running through creative problem-solving. When he joined the army, his mechanical background made him a natural fit for the Armored Corps, and he was assigned to tank maintenance training. The Canadian Army taught standardized maintenance procedures based on following technical manuals and using specified parts, which frustrated Mlynarczyk. He understood why standardization was important for large organizations, but he also knew that combat would create situations where standard procedures wouldn't work. By 1944, Mlynarczyk was a sergeant with the 1st Hussars, a regiment equipped with Sherman tanks that had landed in Normandy in July. He had spent 6 weeks maintaining tanks under combat conditions, and he'd learned that battlefield maintenance was completely different from the training he'd received. Proper parts weren't always available, repairs had to be done under enemy fire, and crews needed their tanks operational immediately, regardless of whether repairs met specifications. Mlynarczyk had already improvised dozens of field repairs that technically violated regulations, but kept tanks running when standard procedures would have left them deadlined. His commanding officers tolerated these improvisations because they worked, and because operational necessity trumped adherence to maintenance doctrine. On the evening of August 7th, Mlynarczyk attended a briefing where officers explained the upcoming assault on German positions in the Falaise pocket. The intelligence officer showed aerial photographs of the German defensive positions, and what Mlynarczyk saw was deeply troubling. The Germans had fortified every stone building and farmhouse, creating a network of mutually supporting strongpoints that dominated the approaches. Tank officers described their previous attempts to destroy these positions using high-explosive shells, and the results had been discouraging. The Norman stone walls were incredibly thick and well-constructed, absorbing artillery hits without significant damage. Infantry officers described attacks where their men had been pinned down for hours by machine gun fire from positions that seemed invulnerable. Someone asked about flamethrower support, and the response was that no Crocodiles were available for the Canadian sector. The regiment would attack with conventional Shermans and infantry, accepting the casualties that this approach would inevitably produce. After the briefing, Mlynarczyk returned to the maintenance area and spent several hours thinking about the problem. The Crocodile's effectiveness wasn't mysterious. It projected burning fuel that penetrated fortifications through openings and forced defenders to evacuate. The mechanical principles were straightforward: pressurized fuel storage, a pump system to build pressure, and a projection nozzle to direct the stream. The British had developed a sophisticated system with armored trailers and specialized equipment, but the basic function wasn't inherently complicated. Mlynarczyk started sketching rough diagrams of how a simplified flame projector might work using components available in the maintenance area. The Sherman tank had several features that might be adapted. The bow machine gun mount provided a forward-facing opening, compressed air systems existed for various tank functions, and fuel was obviously available. The challenge was creating sufficient pressure to project the fuel stream far enough to be tactically useful, and doing it safely enough that the tank crew wouldn't be endangered. By 3 a.m. on August 8th, Mlynarczyk had a rough design concept, and he knew he needed help from other mechanics who understood fabrication. He woke Corporal James Mackenzie, a welder from Nova Scotia, who had been fabricating armor patches and repair brackets for damaged tanks. Mlynarczyk explained his idea, showed Mackenzie the sketches, and asked if they could build a working flame projector in less than 24 hours. Mackenzie was skeptical but intrigued, and he pointed out several obvious problems with the design as sketched. The pressure required to project fuel 40 or 50 yards would need a robust pump system. The fuel mixture would need to ignite reliably, and the entire system would need to fit inside or outside a Sherman without compromising the tank's combat capability. Most critically, if anything went wrong, they could create a death trap that would incinerate their own crews. Mlynarczyk acknowledged these concerns, but argued that doing nothing guaranteed Canadian infantry would die assaulting positions that tanks couldn't neutralize. If there was even a chance of creating a weapon that could help, they had to try, and they could test the system thoroughly before risking it in combat. Mackenzie agreed to help, and they woke two other mechanics, Corporal Robert Dubois and Private William Harrison, both skilled with fabrication and mechanical systems. The four men spent the early morning hours surveying available materials and components that might be adapted to create a flame projection system. The first critical component was fuel storage, and they identified several 50-gallon drums that had been used for various purposes, including transporting water and lubricants. These drums could be cleaned and used to store the flame fuel mixture, and they could be mounted externally on the tank's rear deck, where they wouldn't interfere with internal systems. External mounting also meant that if the fuel ignited accidentally, it would burn outside the crew compartment rather than inside. The second component was a pressure system, and here they found a solution in the Sherman's own compressed air system. The tank used compressed air for various functions, including starting engines and operating certain controls, and the air compressor could generate pressures exceeding 100 psi. If they could route compressed air into the fuel drums, the pressure would force fuel through a projection line toward the target. This was simpler than building a dedicated fuel pump and used existing tank systems, reducing the amount of custom fabrication required. The third component was the projection nozzle and ignition system, and this proved to be the most challenging aspect. They needed a nozzle that could direct the fuel stream accurately, and they needed a reliable way to ignite the fuel as it left the nozzle. Milnarczyk proposed using the Sherman's bow machine gun mount, which could be modified to accept a projection nozzle instead of the .30 caliber machine gun. This location provided a forward-facing projection angle, and the existing ball mount allowed for traverse and elevation adjustments. For ignition, they considered several options, including electrically activated spark systems, but the simplest solution was a pilot light system. A small continuous flame at the nozzle exit would ignite the fuel stream as it passed, similar to how acetylene torches worked. By dawn on August 8th, the four mechanics had a conceptual design and a parts list, and they began the actual fabrication work. They selected a damaged Sherman that had been hit by anti-tank fire and was awaiting depot repair, and they would use this tank as their test platform. The tank's combat systems were mostly intact despite the damage, making it suitable for testing modifications before transferring them to operational vehicles. Mackenzie began fabricating the external fuel storage mounts, welding brackets that would secure two 50-gallon drums to the tank's rear deck. The drums needed to be positioned where they wouldn't interfere with turret rotation or engine access, but close enough to minimize the length of fuel lines running forward. He also fabricated quick-release mechanisms so the drums could be jettisoned if they were hit or if fire spread to them. Dubois worked on the compressed air routing system, tapping into the Sherman's air compressor output and running steel lines back to the fuel drums. The airlines needed pressure regulation valves to control the fuel flow rate, and they needed check valves to prevent backflow if pressure was lost. He salvaged these components from damaged vehicles and assembled them into a functional pressure control system. Harrison fabricated the projection nozzle assembly, starting with a piece of steel pipe that would replace the bow machine gun in its ball mount. The pipe's internal diameter needed to be sized correctly. Too small and the fuel wouldn't flow fast enough. Too large and the pressure wouldn't project it far enough. Through trial and error with water tests, they determined that a 3-4-inch pipe provided good results, projecting a stream about 40 yards at available pressures. At the nozzle exit, Harrison fabricated a spark screen that would hold a pilot light flame, and the pilot light was fed by a small propane line from a portable cylinder. Milnarczyk coordinated the work and solved problems as they arose, and the biggest challenge was ensuring all components worked together as a system. Fuel had to flow from the drums through steel lines to the projection nozzle. Pressure had to be sufficient, but not so high it burst the lines, and ignition had to be reliable. By mid-afternoon on August 8th, they had assembled the major components and were ready for initial testing. The first tests used water instead of flammable fuel to verify the pressure system worked and that the projection range was adequate. With the air compressor running and pressure set to 80 psi, they opened the control valve and water sprayed from the nozzle in a solid stream. The range was approximately 35 yards, less than a Crocodile's 120-yard range, but potentially sufficient for the close-range fighting expected in Normandy's villages. They experimented with different pressure settings and nozzle configurations, eventually achieving a consistent 40-yard range with good accuracy. The next test was more dangerous. They needed to verify the system would work with actual fuel, and that ignition was reliable. The fuel mixture for flame weapons wasn't simply gasoline, as straight gasoline burned too quickly and didn't stick to targets effectively. British Crocodile tanks used a mixture of gasoline, diesel fuel, and a thickening agent that created a napalm-like substance that stuck to surfaces and burned intensely. Milnarczyk didn't have access to proper thickening agents, but he knew that diesel fuel mixed with gasoline in the right proportions would create an adequately sticky burning mixture. They mixed 1 drum of fuel using approximately 60% diesel and 40% gasoline, and this mixture was thick enough to flow through the projection system, but viscous enough to cling to targets. For the ignition test, they positioned the tank facing an open area well away from other vehicles and equipment, and only Milnarczyk would operate the system during the test. If something went wrong, he didn't want anyone else endangered, and he had prepared fire extinguishers and emergency procedures in case the test failed catastrophically. At 4:30 p.m. on August 8th, Milnarczyk climbed into the driver's position of the modified Sherman, started the engine, and lit the pilot light at the projection nozzle. The small propane flame burned steadily at the nozzle exit, and he could see it flickering through the bow vision port. He opened the compressed air valve gradually, building pressure in the fuel drums, and when the pressure gauge showed 70 psi, he opened the fuel control valve. The fuel mixture sprayed from the nozzle, passed through the pilot flame, and ignited instantly into a stream of fire that reached out 40 yards across the test field. The flames were orange and yellow with black smoke, and they burned with a roaring sound that could be heard over the tank engine's rumble. Milnarczyk kept the fuel flowing for about 5 seconds, then closed the control valve, and the flames died immediately as the fuel stream stopped. He climbed out of the tank, checked for any signs of fire or fuel leaks, and found everything functioning properly. The test had succeeded. They had created a working flame projector from salvaged parts and standard tank components in less than 24 hours. Mackenzie, Dubois, and Harrison, who had been watching from a safe distance, ran over to examine the system and congratulate Milnarczyk on the successful test. But success in testing didn't mean the system was ready for combat, and Milnarczyk knew they needed to address several issues before the modification could be used operationally. The first issue was range. 40 yards was workable but marginal, and they needed to see if they could extend it without creating dangerous pressure levels. The second issue was fuel capacity. The two 50-gallon drums provided only 100 gallons total, which would allow perhaps 30 to 40 seconds of continuous flame projection. That wasn't much endurance for a weapon system, though the Crocodile's 400 gallons only provided about 2 minutes of continuous operation. The third issue was crew safety. The external fuel drums were vulnerable to enemy fire, and if they were penetrated, the burning fuel could spread across the tank. The fourth issue was tactical employment. Tank commanders needed to understand how to use the flame projector effectively and what its limitations were. Milnarczyk decided they needed to conduct more extensive testing and then brief the regiment's officers before modifying any operational tanks. So over the next several hours, they conducted multiple test firings, experimenting with different fuel mixtures, pressure settings, and projection techniques. They discovered that increasing the pressure to 90 psi extended the range to approximately 50 yards, but also increased fuel consumption significantly. They found that short bursts of flame lasting 2 to 3 seconds were more effective than continuous streams because they conserved fuel and created intense local heating. They also discovered that the flame projected slightly upward at longer ranges due to the mounting angle, which actually proved advantageous for targeting building upper floors. By evening on August 8th, Milnarczyk felt confident enough in the system to brief Major James Campbell, the regiment's second-in-command. Campbell was known as a pragmatic officer who valued results over strict adherence to regulations, and Milnarczyk hoped he would support the improvised weapon. Milnarczyk explained what they had built, demonstrated the system with a test firing, and outlined the tactical applications he envisioned. Campbell watched the demonstration with obvious interest, and when Milnarczyk finished, Campbell asked direct questions about safety, reliability, and what would happen if the fuel drums were hit. Milnarczyk answered honestly. The system was safer than it appeared, because the external mounting meant fires would burn outside the crew compartment. If the fuel drums were hit by enemy fire, the quick-release mechanism allowed the crew to jettison them immediately, and the fuel lines had shut-off valves to prevent continued leakage. Reliability was good based on testing, though the system was simple enough that field repairs could fix most problems. Campbell considered this information and then made a decision that showed why he was respected by his men. He would authorize the modification of 3 Sherman tanks as an experiment. If the flame-equipped tanks proved effective in the upcoming operation, they would modify more vehicles. But if the system proved dangerous or ineffective, they would remove it immediately. Campbell also insisted that only volunteer crews would operate the modified tanks, as the added risk from carrying external fuel drums had to be accepted willingly. Finally, Campbell would personally brief the regimental commander, Colonel Gordon Wotherspoon, and take responsibility for authorizing the unauthorized modifications. With Campbell's approval secured, Milnarczyk and his team began working through the night to modify 3 operational Sherman tanks. They selected tanks that were scheduled to participate in the next day's assault and whose crews had volunteered to test the flame system. The modification work proceeded faster now that they understood the process, and each tank took approximately 6 hours to convert. By dawn on August 9th, 3 Sherman tanks equipped with improvised flame projectors sat in the maintenance area ready for combat testing. The tank commanders received briefings on how to operate the flame system, and Milnarczyk emphasized the importance of using short bursts rather than continuous flames. He explained that the flames were most effective against firing ports, windows and other openings where they could penetrate into defended spaces. He also warned that the flame projector's 50-yard range meant they had to get dangerously close to targets, well within effective range of German anti-tank weapons. The crews understood the risks, but also understood that their flame-equipped tanks might prevent infantry casualties that conventional tanks couldn't prevent. At 9:00 a.m. on August 9, 1944, the 1st Hussars began their assault on German positions near Saint-Aignan-de-Craménil, a small village that anchored the German defensive line. The 3 flame-equipped Shermans advanced in the second wave, following conventional tanks that would suppress enemy positions with high explosive fire. The first German strongpoint was a stone farmhouse that had been converted into a fortress, with walls reinforced by sandbags and firing ports cut through the ancient stone. Conventional Shermans had been firing at this position for 30 minutes without effect, and Canadian infantry was pinned down 200 yards away by machine gun fire. Sergeant Thomas Mitchell commanded the first flame-equipped Sherman to engage the target, and he maneuvered his tank to within 50 yards of the farmhouse. This was suicidally close by normal tank combat standards, but it brought the farmhouse within range of the flame projector. Mitchell's bowgunner, Corporal David Ross, operated the flame system, and he aimed the projection nozzle at a firing port on the farmhouse's ground floor. When Mitchell gave the order, Ross opened the fuel valve and a stream of burning fuel arced across the 50 yards and struck the farmhouse wall around the firing port. The flames splashed against the stone and streamed through the firing port into the building's interior, and black smoke began pouring from windows and openings. Ross maintained the flame for about 4 seconds, then shut off the flow, and Mitchell backed his tank away to a safer position. Within 30 seconds, German soldiers began running from the farmhouse, some with their uniforms smoking, and they surrendered immediately to the advancing Canadian infantry. The entire German position, which had held up the Canadian advance for hours, was neutralized in less than a minute by one burst of flame. The psychological effect was exactly what the British had reported with their Crocodiles. Defenders would not remain in positions that could be burned out. The 2nd and 3rd flame tanks engaged similar targets, with equally dramatic results, and within 2 hours, the Canadian advance had broken through German positions that conventional weapons couldn't neutralize. Word of the improvised flame tanks spread rapidly through the regiment, and tank commanders who had been skeptical now demanded that their vehicles receive the modification. By the evening of August 9th, Colonel Wotherspoon had authorized modification of all available Sherman tanks in the regiment, and Milnarchik's maintenance team was working around the clock to install the systems. The work proceeded in assembly line fashion now that procedures were established, and each tank required approximately 4 hours to modify. By August 11th, the 1st Hussars had 24 flame-equipped Sherman tanks, giving the regiment capabilities that no Canadian unit had previously possessed. The improvised flame tanks participated in multiple actions during the Falaise pocket operations, and their effectiveness exceeded even optimistic expectations. German defensive positions that would have required prolonged infantry assaults with heavy casualties were neutralized quickly with minimal Canadian losses. The flames proved particularly effective against the stone buildings that characterized Norman architecture, as the intense heat penetrated through firing ports and ventilation openings. On August 12th, during the attack on Claire-Tizon, Lieutenant Charles Harrison's flame tank engaged a fortified manor house that dominated the approach to the village. The manor had walls over 3 feet thick, multiple firing positions, and had held up the Canadian advance for an entire day despite artillery bombardment. Harrison maneuvered his tank to within 40 yards, exposing his vehicle to close-range anti-tank fire, and his bowgunner projected flames through a large window on the ground floor. The flames penetrated deep into the building's interior, and smoke began pouring from every opening within seconds. German defenders evacuated the manor immediately, and Harrison's tank had neutralized in 20 seconds what artillery couldn't destroy in a full day of bombardment. The improvised flame systems did experience problems during combat operations, and these challenges revealed the limitations of field-expedient weapons. The external fuel drums were vulnerable to enemy fire, and on August 13th, Corporal Michael O'Brien's tank took a hit from a German anti-tank gun that penetrated one of the fuel drums. The crew immediately activated the quick-release mechanism, jettisoning the damaged drum before the fuel could ignite, and the tank survived with only minor damage. This incident validated Milnarchik's safety design, demonstrating that the external mounting protected the crew even when the fuel storage was hit. Another challenge was fuel consumption. The 100-gallon capacity provided only about 8 to 10 engagements before tanks had to return for refueling. Milnarchik's team addressed this by positioning fuel supply points closer to the fighting, and they trained crews to use fuel efficiently through careful aim and short bursts. Mechanical failures occurred periodically, usually involving pressure regulation valves or fuel line connections that loosened from vibration. But these problems were easily fixed in the field, and Milnarchik's team accompanied the regiment to provide immediate maintenance support. The tactical doctrine for employing the flame tanks evolved rapidly through combat experience, and tank commanders learned optimal engagement techniques. The most effective approach was to use conventional tanks to suppress enemy positions, with high explosive fire while flame tanks maneuvered to close range. Once within 50 yards, flame tanks would project short bursts through any openings visible in the fortifications, and the intense heat and smoke would force defenders to evacuate. Infantry would follow immediately behind the flame tanks to capture surrendering German soldiers and secure the positions. This combined arms approach proved devastatingly effective, allowing Canadian forces to advance through heavily fortified areas faster than German defenders expected. By mid-August, other Canadian units had learned about the 1st Hussars' improvised flame tanks, and requests for similar modifications flooded higher headquarters. The 2nd Canadian Armoured Brigade authorized Milnarchik to brief mechanics from other regiments on the modification procedures, and soon multiple Canadian tank units were building their own versions. Each regiment introduced minor variations based on available materials and specific requirements, and some improvements emerged from this distributed development. The Fort Garry Horse added a 3rd fuel drum to extend endurance. The Sherbrooke Fusiliers developed an improved nozzle design that increased range to 60 yards, and the South Alberta Regiment created a more sophisticated ignition system. This grassroots innovation spread through the Canadian Armoured Forces faster than any official equipment program could have achieved. British forces became aware of the Canadian improvised flame tanks by mid-August, and their reaction was complex. On one hand, British officers were impressed by the Canadian ingenuity and the effectiveness of the field expedient systems. On the other hand, they were concerned that unauthorized modifications violated proper procedures and created potential safety hazards. The 79th Armored Division, which controlled all official British flamethrower tanks, sent a technical team to inspect the Canadian modifications. The British engineers examined Milnarchik's design, conducted their own tests, and submitted a report that acknowledged the system worked but didn't meet official standards. However, the report also noted that the Canadian improvisation was filling a tactical need that British equipment allocations hadn't addressed. The British Army's response was pragmatic. They wouldn't officially approve the modifications, but they wouldn't order them removed as long as they proved effective and safe. This unofficial tolerance allowed Canadian units to continue using and developing their improvised flame systems throughout the Normandy campaign. American forces also learned about the Canadian flame tanks, and several U.S. tank battalions requested information about the modifications. The U.S. Army had its own flamethrower systems, but these were typically mounted on light tanks or specialized vehicles rather than standard Shermans. Some American units experimented with Canadian-style modifications, though the practice never became as widespread in U.S. forces as it did among Canadians. The Falaise Pocket operation concluded in late August 1944 with the destruction of major German forces in Normandy, and Canadian forces played a crucial role in closing the pocket. The improvised flame tanks contributed significantly to the speed of the Canadian advance by neutralizing strongpoints that would otherwise have required costly infantry assaults. After the Falaise victory, Canadian forces advanced rapidly toward the Seine River and then into Belgium, and the tactical situation changed dramatically. The fighting became more mobile with fewer static defensive positions, and the utility of flame weapons decreased as the Germans lost their ability to conduct prepared defenses. By September 1944, most Canadian tanks had the flame systems removed because the external fuel drums created unnecessary vulnerability in mobile warfare. However, some units retained modified tanks for specific operations where fortifications might be encountered, and the systems remained available for reinstallation if needed. Sergeant Andrew Milnarchik continued serving with the 1st Hussars through the liberation of the Netherlands and into Germany. He was promoted to warrant officer in October 1944 in recognition of his technical contributions, though his flamethrower innovation was never officially acknowledged in his service record. The improvised flame systems he developed saved countless Canadian lives during the Falaise operations, but because the modifications were unauthorized, they couldn't be officially recognized. Milnarchik didn't seem to care about official recognition, as he was satisfied knowing his innovation had helped his comrades survive battles that might otherwise have killed them. Milnarchik didn't seem to care about official recognition, as he was satisfied knowing his innovation had helped his comrades survive battles that might otherwise have killed them. After the war ended in May 1945, Milnarchik returned to Canada and resumed his pre-war occupation as a mechanic in Winnipeg. He worked on farm equipment and diesel engines for nearly 40 years, rarely discussing his wartime service, except with fellow veterans who understood the context. The story of the improvised flame tanks remained largely unknown outside the Canadian armored community for decades after the war. Official Canadian Army histories of the Normandy campaign mentioned flame-equipped tanks, but didn't detail their improvised nature or credit Milnarchik's innovation. British histories focused on the Churchill Crocodile and other official flamethrower systems, with only passing references to Canadian field modifications. The improvised nature of the Canadian flame tanks meant they existed in a grey area of military documentation. They were used extensively, but never officially approved. In the 1970s, military historians researching Canadian armoured operations in Normandy began uncovering references to flame-equipped Shermans in unit war diaries. These references were often cryptic, mentioning special equipment or field modifications without providing technical details. Historian Terry Kopp, researching the 1st Hussars operations during Falaise, found multiple diary entries describing flame attacks against German positions. Kopp interviewed surviving veterans from the regiment, and several remembered the improvised flame tanks vividly. Lieutenant Charles Harrison, who had used a flame tank to neutralize the manor house at Clare-Tizon, described the system in detail and credited Milnarczyk with its development. Kopp tracked down Milnarczyk in 1978 and interviewed him extensively about the Flamethrower project. Milnarczyk was 65 years old by then, still working part-time as a mechanic, and he was characteristically modest about his wartime innovation. He explained that the improvised flame system wasn't particularly sophisticated or original, just a practical solution to an immediate problem. When Kopp suggested that the innovation had saved many Canadian lives, Milnarczyk acknowledged that possibility, but emphasized the contributions of the tank crews who actually used the systems in combat. Kopp's research resulted in a detailed article published in Canadian Military History Journal in 1982, bringing the story to broader attention. The article documented the technical details of Milnarczyk's design, the operational effectiveness of the improvised flame tanks, and the tactical impact during falaise. Military engineers reading the article were impressed by the elegance of the solution, using existing tank systems to minimize custom fabrication and external mounting to enhance safety. The design reflected practical mechanical knowledge combined with understanding of combat requirements, exactly the kind of innovation that field forces needed, but official development programs often failed to provide. The story also highlighted broader themes about military innovation and the role of improvisation in warfare. Official weapons development programs follow established procedures. Requirements are defined, designs are developed, prototypes are tested, and production is authorized. This process ensures quality and safety, but takes time, often years from concept to fielding. Field improvisation works differently. Immediate needs drive rapid solutions using available materials, and testing occurs under actual combat conditions. The results aren't as polished as official programs, but they're available immediately when needed most. Milnarczyk's Flamethrower represented this alternative approach to military technology, solving a tactical problem through ingenuity rather than bureaucratic process. The Canadian Army's response to the improvised flame tanks also revealed institutional attitudes toward unauthorized innovation. Officially, the modifications violated regulations and should have been forbidden, but practically they filled a critical capability gap. Canadian commanders chose pragmatism over doctrine, allowing the modifications to continue because they worked and because operational necessity outweighed regulatory compliance. This flexibility reflected a broader Canadian military culture that valued practical results and was willing to bend rules when circumstances justified it. The contrast with British approaches was instructive. British forces had superior official flamethrower systems, but lacked the flexibility to allocate them where Canadians needed them. Canadian forces lacked official systems, but had the flexibility to create their own solutions when official support wasn't available. Neither approach was inherently superior, but the Canadian experience demonstrated that military organizations need both formal development and informal innovation. Modern military analysis of Milnarczyk's innovation has focused on several aspects that remain relevant to contemporary warfare. First, the importance of technical knowledge at the tactical level. Milnarczyk succeeded because he understood both mechanical principles and combat requirements. Modern militaries invest heavily in training technical specialists, but they don't always encourage the kind of creative problem-solving that Milnarczyk demonstrated. Second, the value of allowing field modifications when circumstances require them. Rigid adherence to approved equipment lists can prevent forces from adapting to unexpected challenges. Modern doctrine increasingly recognizes the need for flexibility, though tensions between standardization and adaptation continue. Third, the effectiveness of distributed innovation where multiple units develop variations on a basic concept. The Canadian flame tank modifications spread through informal networks faster than any formal program. Modern militaries struggle to replicate this kind of rapid distributed development within institutional frameworks that emphasize centralized control. The technical aspects of Milnarczyk's design also provide insights into effective improvisation principles. He succeeded partly because he leveraged existing systems rather than creating everything from scratch. The compressed air system, the bow gun mount, and available fuel drums. This approach minimized custom fabrication and used components that were already proven reliable in the tank environment. Modern engineers call this system integration rather than system design, and it's often faster and more reliable than developing entirely new systems. Mlynarchik's safety considerations also demonstrated good engineering judgment. External fuel mounting, quick-release mechanisms, and shut-off valves all reduced risks to acceptable levels. He didn't eliminate all risks, which would have been impossible, but he reduced them sufficiently that the tactical benefits outweighed the dangers. This balance between risk and benefit is fundamental to military engineering, but difficult to achieve in practice. The operational impact of the improvised flame tanks can be quantified through analysis of Canadian casualty rates during the Falaise operations. Canadian units equipped with flame tanks experienced significantly lower infantry casualties when assaulting fortified positions compared to units without flame support. The 1st Hussars, which had 24 flame-equipped tanks by mid-August, reported infantry casualty rates approximately 60% lower than similar operations conducted before the flame systems were available. This dramatic difference reflected the effectiveness of flame weapons against fortified positions and validated Mlynarchik's original assessment of the tactical need. The speed of Canadian advances also increased measurably once flame tanks became available, as strong points were neutralized quickly rather than requiring prolonged reduction efforts. Operations that might have taken days with conventional weapons were completed in hours, and this acceleration contributed to the successful closure of the Falaise pocket. The psychological impact on German defenders was also significant, as survivors reported that flame attacks created panic and destroyed morale. German soldiers would endure artillery bombardment and tank fire, but flame weapons triggered immediate evacuation because the prospect of burning to death was psychologically unbearable. This psychological effect was as important as the physical destruction the flames caused, and it exemplified how weapon effectiveness depends on both material and moral factors. After the war, military historians debated whether official development programs could have provided Canadian forces with flamethrower capabilities if different decisions had been made. The British Crocodile program had demonstrated the effectiveness of flamethrower tanks, and in theory, Canadian forces could have requested allocation of these systems earlier. However, the reality of Allied command structures meant that British-controlled specialized equipment went first to British units, and Canadian requests had lower priority. Alternative approaches might have included Canadian development of their own official flamethrower program, but this would have required resources and time that weren't available in 1944. The practical reality was that Mlynarchik's improvised solution provided capabilities when and where they were needed, filling a gap that official programs hadn't addressed. This doesn't mean improvisation should replace formal development, but it demonstrates that field forces need both official equipment and the flexibility to create their own solutions. The comparison between Mlynarchik's improvised system and the British Crocodile is instructive because it highlights different engineering priorities. The Crocodile was optimized for performance, maximum range, maximum fuel capacity, and integration with the Churchill tank's armor. Mlynarchik's system was optimized for feasibility, using available materials, minimizing fabrication time, and achieving adequate performance rather than maximum performance. The Crocodile was objectively superior in almost every technical measure, but Mlynarchik's system had the decisive advantage of availability when needed. This trade-off between optimal performance and practical availability appears repeatedly in military history, and understanding it helps explain why improvised solutions sometimes prove more effective than superior official systems. The story of the Canadian improvised flame tanks also intersects with broader questions about military innovation and institutional resistance to change. Mlynarchik faced skepticism from officers who questioned whether unauthorized modifications should be allowed, and he succeeded partly because sympathetic commanders like Major Campbell supported experimentation. Military organizations need this kind of commander support for innovation because junior personnel rarely have authority to implement unconventional solutions without approval. Campbell's willingness to authorize the modifications and accept responsibility for any failures was crucial to the project's success. Modern military organizations recognize this dynamic and attempt to create environments that encourage innovation, but institutional cultures often resist approaches that deviate from established procedures. Finding the right balance between control and flexibility remains an ongoing challenge for military institutions. The educational value of Mlynarczyk's story extends beyond the specific technical details of flamethrower construction. Military engineering programs use the Canadian flame tank case study to teach principles of rapid prototyping, systems integration, and field adaptation. Students analyze the design decisions Mlynarczyk made, discuss the trade-offs he accepted, and consider how similar approaches might apply to contemporary challenges. The case also illustrates the importance of understanding operational requirements. Mlynarczyk succeeded because he understood what tank crews needed to neutralize fortified positions. Many technical specialists focus on engineering excellence without sufficient attention to operational context, producing systems that work technically but don't address actual tactical needs. Mlynarczyk's approach reversed this priority. He started with the tactical problem and developed a technical solution that adequately addressed it. Andrew Mlynarczyk died in 1994 at age 81, and his obituary in the Winnipeg Free Press mentioned his wartime service but didn't detail his flamethrower innovation. His family knew he had been a tank mechanic in the war, but they didn't fully understand the significance of what he had accomplished until historians contacted them years later. In 2004, the Royal Canadian Armoured Corps Museum in CFB Gagetown created an exhibit featuring the improvised flame tank modifications. The exhibit included technical drawings based on surviving photographs and veteran testimony, demonstrating how the systems were constructed and operated. A replica of the fuel drum mounting system was fabricated and displayed on a Sherman tank, giving visitors a sense of how the modifications looked. The exhibit explicitly credited Mlynarczyk and his team for the innovation, finally providing official recognition that had been absent during the war. Mlynarczyk's son attended the exhibit opening and spoke about his father's character and approach to mechanical problems. He described his father as someone who believed that most problems had solutions if you were willing to think creatively and work with available resources. This philosophy had served Mlynarczyk throughout his life, from maintaining farm equipment in the Depression to keeping tanks operational in Normandy. The recognition came too late for Mlynarczyk to appreciate, but it ensured that his contribution to Canadian military history would be remembered. In recent years, military historians have placed Mlynarczyk's innovation in broader context by comparing it to similar field modifications from other militaries and conflicts. The pattern of field forces improvising solutions when official support is inadequate appears repeatedly throughout military history. During World War II alone, examples include American soldiers welding additional armor to tanks in Italy, Soviet troops mounting aircraft rockets on tanks, and German crews adapting captured weapons. More recent conflicts show similar patterns: improvised armor on vehicles in Iraq, field-expedient drone countermeasures in Syria, and adapted commercial technology in Afghanistan. The common thread is that combat creates challenges that official equipment programs haven't anticipated, and field forces must adapt to survive. Mlynarczyk's flamethrower stands out because of its effectiveness and the speed with which it was developed and deployed, but the underlying dynamic is universal. The technical simplicity of Mlynarczyk's design is also noteworthy because it demonstrates that effective solutions don't require sophisticated technology. The improvised flame projector used compressed air, fuel drums, steel pipes, and basic valves, components that were available in 1944 and remain available today. Modern flame weapons are far more sophisticated, but the basic principles Mlynarczyk employed remain valid. This suggests that effective innovation often depends more on creative application of existing technology than on development of new technology. The legacy of Canadian improvised flame tanks extends beyond their specific tactical impact in Normandy. They demonstrated that field forces equipped with technical knowledge and supported by flexible commanders can develop effective solutions to unexpected problems. This capability for rapid adaptation is increasingly recognized as essential for modern military forces operating in complex, unpredictable environments. Military doctrine now explicitly includes concepts like mission command and adaptability, recognizing that centralized control can't address all situations forces encounter. Mlynarchik's story provides a concrete historical example of these principles in action, demonstrating both the potential and the challenges of decentralized innovation. The question for modern militaries is how to create organizational cultures that enable this kind of innovation while maintaining necessary standards and safety. The answer isn't simple, as the tensions between flexibility and control, innovation and standardization remain difficult to resolve. But Mlynarchik's example suggests that success requires commanders willing to accept calculated risks, specialists with broad technical knowledge, and institutional tolerance for unconventional approaches. In the final analysis, Sergeant Andrew Mlynarchik's improvised flamethrower represents something larger than one technical innovation in one campaign. It represents the principle that military effectiveness depends not just on official equipment and doctrine, but on the creativity and initiative of individual soldiers. Mlynarchik saw a problem that threatened his comrades' lives, recognized that official solutions weren't available, and created his own solution using knowledge and resources at hand. His innovation saved Canadian lives, accelerated operations, and demonstrated that sometimes the best military technology comes not from laboratories, but from mechanics who refuse to accept that problems are unsolvable. The burning walls of Norman farmhouses and the surrendering German soldiers testified to the effectiveness of one mechanic's stupid idea. That idea, developed in 36 hours from spare parts and improvisation, proved as effective as sophisticated systems that required years to develop. This isn't to diminish the value of formal development programs, which remain essential for equipping modern forces, but it does suggest that military organizations need both official programs and informal innovation, both standardized procedures and creative adaptation. Mlynarchik's flamethrower existed in the gap between what official systems provided and what tactical situations required. That gap will always exist because warfare is unpredictable and complex, creating challenges that no development program can fully anticipate. The military forces that succeed will be those that empower their personnel to bridge that gap through innovation, adaptation, and creative problem-solving. If you found this story as compelling as we did, please take a moment to like this video, as it helps us share more forgotten stories from the Second World War. Subscribe to stay connected with these untold histories, because each one matters, and each one deserves to be remembered. And we'd love to hear from you, so leave a comment below telling us where you're watching from,